What's up, everybody? Welcome to Kenny Kinetics, where learning is made easy. Let's go. So, in this video, we're going to talk about EKGs. And first, I'm going to start off with the correlation between the EKG waves and the cardiac conduction cycle that we learned about in the last video. And then we're going to get into how to interpret EKGs. So, let's go. Let's get it. Alright, everybody, let's get started. So like I said in the last video, we talked about the cardiac conduction cycle and how the electrical signal goes through the heart. And now we're going to correlate that with EKGs. So an EKG is basically used to determine if there are any abnormalities that are being seen within the heart and the electrical conduction going throughout the heart. So an EKG can pick up on this, and that's how we can diagnose people with stuff like a heart attack or angina or atherosclerosis, coronary artery disease, stuff like that. There are things that will show up in the EKG that we can see to help us determine what's going on in the heart. So here I have a little animation drawn out for you to correlate the cardiac conduction with the EKG waves. So again, as we learned in the last video, the SA node will send the signal to the left atrium through Bachmann's bundle. And when the SA node sends that signal to the left atria, the atrias together, they start to depolarize. And that depolarization of the atria correlates with the P wave. So the P wave on the EKG right here is the atria depolarizing. So after the atria depolarize, they start to contract. And when they start to contract, they start to release blood from both of the atrias into the ventricles. So this again still corresponds with the P wave. When the atria depolarize and when the atria contract, the P wave shows up on the EKG. So as we know from the last video, the depolarization from the SA node also goes down to the AV node through the internodal pathways. And the job of the AV node is to say, hold up, wait a minute, stop that signal to allow for all of the blood from the atria to go into the ventricles. So when that AV nodal delay occurs, that corresponds to the P to R segment on the EKG. So after that AV nodal delay, all the blood from the atria are now in the ventricle. That AV nodal delay again is key because 20% of blood from the atria go into the ventricles after that contraction. Without it, only 80% of the blood would be going from the atria into the ventricles. So after the atria contract and all the blood's in the ventricles, the AV node is done with its delay, and it's going to send that signal down into the left and the right bundle branches. And that signal is going to continue through the left and the right bundle branches to the Purkinje fibers around the ventricles. So when that signal starts from the AV node down through the bundle of His, which is the left and right bundle branches, to the Purkinje fibers, this is when the ventricles depolarize. So again, that signal is getting stronger and stronger and stronger as it is coming around the ventricles. And as the ventricles depolarize, you get this deflection here, which is called the QRS wave. The QRS wave corresponds to that ventricular depolarization that's going on here. While the ventricles are depolarizing, the atria are beginning to relax and they are repolarizing. So during this QRS deflection, we see ventricular depolarization, but the reason why we don't see atria Repolarization is because this deflection is just so great that it gets buried within the QRS wave. But just know that when the ventricles are depolarizing here, the atria are repolarizing. So once the ventricles depolarize, they start to contract. So now the whole ventricle, both of them, are squeezing together, contracting as a unit, which will eventually build up the pressure within the ventricles and then allow for blood to go into the pulmonary trunk and the aorta. So when the ventricles begin to contract on the EKG, this corresponds to the ST segment. Now, if you have a myocardial infarction, aka a heart attack, this ST segment will be elevated. And when I make a video on heart attacks and stuff, you'll see that depicted later. And say if someone has like ischemia going on, ischemia means a lack of oxygen, this ST segment will be depressed. So it'll be below. There's a line on the EKG that's called the isoelectric line. So the ST segment will be below it, and that signifies myocardial ischemia. So after the ventricles eject their blood into the pulmonary trunk and the aorta, the ventricles will begin to relax. And this is going to start ventricular diastole. And when the ventricles begin to relax, you see this wave appear, which is called the T wave. And this signifies, again, ventricular repolarization because the ventricles begin to relax, their pressure starts to decrease, and that allows for the pressure within the ventricles to decrease. And while that's occurring, the atria are starting to contract and their pressure is rising within the atria until the pressure in the atria is greater than the pressure in the ventricles, which will cause for contraction to occur, and then the cycle will repeat on and on and on. So just for you visual learners out there, here's the animation just played through. The first thing that happens is that the signal comes from the SA node to the left atria, and then they begin to depolarize, which brings up this deflection up here, which is the P wave. Then they send the signal through the internodal pathways to the AV node. That AV nodal delay occurs, which will allow for blood in the atria to go to the ventricles, which corresponds with the P to R segment. Then the ventricles begin to depolarize as the signal goes from the AV node to the bundle of His to the Purkinje fibers, which corresponds to the QRS wave. After that, the ventricles begin to contract as one unit, and the pressure starts to rise within the ventricles, which corresponds to the ST segment. And then once the ventricles eject their blood into the pulmonary trunk and into the aorta, the ventricles begin to relax. And when the ventricles begin to relax, ventricular repolarization, this corresponds with the T wave on the EKG. Alright guys, so now we're transitioning into how to interpret the EKG. So there's some things that we need to go over. There are little boxes within these squares. So if you see this square here, there are 5 little boxes that make up this one square. So one little box equals 0.04 seconds. So that means that 5 little boxes equal 0.20 seconds. So this is important because it's going to help us to be able to calculate the rate of the rhythm and see what the heartbeat of the EKG strip equates to. So 5 big boxes. So if you see here, this is 2, 3, 4, 5. 5 of these big boxes equal 1 second. So 5 big boxes equal 1 second. You see these strips here at the top? These all show 1 second. So in order to interpret EKGs, there are 5 steps. I'm going to go through the 5 steps that I learned that works for me. Hopefully it works for you as well. So the first thing you want to do when you are looking at an EKG strip is you want to see if there are QRS waves present. So number 1, are there QRS waves? So we can see that there are QRS waves uniformly throughout this strip here. So number 1 can get a check. The next thing that we look for is if the rhythm is regular. So is the rhythm regular? So there are a couple of options that could fall along with this category on number 2. A regular rhythm is measured at the point between the top of the R to the next R, etc., etc., etc. So if you have like a caliper or something, usually you can take that caliper and put one of the end here and the other end there. And then once you measure that distance, you can just move the caliper from R to R intervals to see if they match up. And if they do match up throughout the EKG strip, that means that the rhythm is regular. If they don't match up throughout the EKG strip, if they're at different lengths between the R's of the QRSs in each one, then that means that they are irregular. Now there's something called regular irregular, meaning that the distance between the R's are different, but they're the same difference throughout the strip. So hopefully that makes sense. And then the last one is irregular, where it's just all random. They are not the same. Like this one, the next QRS wave could be here. The next one could be all the way over here. There's no pattern to it whatsoever. It's just random. The third thing that we look for is the rate. So what is the rate of the strip? And how we calculate the rate is by looking at how many boxes are between the R's of the QRS waves. So we can go ahead and use this one as an example here. If you see here, there's 1, 2, 3, 4. So there are 4 big boxes located between this R and this R. So one way to calculate it is you'll do 300 divided by 4, which equals, I think, 75. 300 divided by 4, which equals 75. Another way to calculate the rate is to count how many little boxes are between the R to R's. So in order to do that, you'll do 1500 divided by how many little boxes are in between. So we know that there's 5 making up one box. So 5, 10, 15, 20. So we'll do 1500 divided by 20, which also equals 75. So that means that for this particular strip, the rate is 75 beats per minute. The next thing that we look for is the P waves. Are there P waves? Are there P waves? So when you're looking for the P waves here, you want to see if they all look the same before each QRS wave that comes up. Because with some of the heart rates, the P waves can look different. And that means that the signal is coming from a different area of the cardiac conduction cycle. So instead of it being generated from the SA node, it might be generated from the AV node or the bundle of His. And if it is, that means that the P waves before each of the QRSs are going to look different because that potential is being generated by a different playmaker within the cardiac conduction cycle. You also want to look for if the P waves are coming before each of the QRS waves, which, as you can see, all of these P waves, they look the same, and all of these P waves come before the QRSs, so that's a check for that one. And then the last one is just measuring the P to R intervals and the QRS. So P to R interval and the QRS. So the P to R interval, which would be from here to here, should be about 0.12 to 0.20. So this equals about 3 to 5 little boxes. And the QRS wave should be about 0.8 to 0.12. And this equals 3 little boxes. So when you're looking at the strip, you want to see how many little boxes are between the P to R and how many little boxes are the QRS waves. If the P to R interval is longer, that means that it's going to be taking a longer time for contraction to occur. So these are the basic steps that you will use to interpret an EKG. When I follow these steps, I'm able to identify what type of rhythm is going on here. So with this particular strip here, if we follow these steps, we can actually analyze this first strip. So there are Q waves present, so we can give number 1 a check. Is the rhythm regular? We see that they look uniformly throughout. They look like they're evenly spaced out, so that's a check there. We already determined that the rate was 75, so we know for a normal heart rate, it needs to be between 60 to 100 beats per minute. 100 beats per minute. So that's good. There are P waves present, and I know that the P to R interval is between the 3 to 5 little boxes, and the QRS waves are within 3 little boxes. Both of these get a check, and for this specific rhythm here, this will be normal sinus rhythm. Normal sinus rhythm. So this is how a normal strip would look like in someone who doesn't have any problems. So hang in for part 2, where we're going to continue interpreting the different strips and identifying what's going on within the strip. Thanks for watching.